Chapter 28 of Astronomy, the Science of the Heavenly Bodies, by David Todd. The Moon and her Surface. As the sun has always reigned as king of day, so is the moon queen of night. Observation of her phases, now waxing, now waning, with her stately motion always eastward among the stars, began with the earliest ages. Often when near the full she must have been seen herself eclipsed, and much more rarely the occurrence of total eclipses of the sun are certain to have suggested the moon's intervention between earth and sun, shutting off the sunlight completely, because these eclipses never took place except when the moon was in the same part of the sky with the sun. If we watch the nightly march of the moon, we shall find that she travels over her own breadth in about an hour's time. By using a telescope on the stars just eastward or to the left of her, she will now and then be seen to pass between us and a star, on very rare occasion a planet, extinguishing its light with great suddenness, the most nearly instantaneous of all phenomena in nature. Draw a line connecting the cusps or horns of the lunar crescent, and then a line eastward at right angles to this, and it will show the direction of the moon's own motion in its orbit round the earth quite accurately. As the phase advances, note the inside edge of the advancing crescent. This will be quite rough and jagged compared to the outside edge, which is the moon's real contour and relatively very smooth. The position of the inside curve will change from night to night, and it marks the line of sunrise on the moon during the fortnight elapsing between new moon and full. While from full through last quarter and back to new moon, this advancing line marks the region of sunset on the moon. The general shape of this line is never a circle, but always elliptical, and astronomers call it the terminator. All along the terminator, sunlight strikes the lunar surface at a small angle, whether near sunrise or sunset, so that owing to the mountains and other high masses of the moon's surface, the terminator is always a more or less jagged and irregular line. Onward from new moon toward full, the horns of the crescent are always turned upward or eastward. When the general line of the terminator becomes a straight line from cusp to cusp, the moon is said to have reached first quarter or quadrature. Onward toward full, the terminator will be seen to bend the other way, and in about a week's time it will have merged itself with the moon's limb. The moon is then said to be full. Afterward the phase phenomena recur in the reverse order, with third quarter midway between full and new moon again. The phase of the moon, called gibbous, take all way from first quarter to third quarter, except when exactly full. As we know that the moon is, like the earth, a non-luminous body, and shines only by virtue of the sunlight falling upon it, clearly an entire half of the moon's globe must be perpetually illuminated by sunlight. The varying phases, then, are due simply to the part of the illuminated hemisphere which is turned toward us. New moon is entirely invisible because the southward hemisphere is turned wholly away from us, while at full moon we see the lunar disc complete, because we are on the same side of the moon that the sun is, and practically in line with both sun and moon. If we could visit the moon, we should see the earth in exactly complementary phase. At new moon here, we should be enjoying full earth there, and full moon here would be coincident with new or dark earth there. The narrow crescent of new moon here would be the period of gibbous earth there, and it is the reflection of sunlight from this gibbous earth which illuminates the part of the moon but faintly seen at this time, popularly known as the old moon in the new moon's arms. Its greater visibility at some times than at others is due to greater prevalence of clouded area in the reflecting regions of the earth turned towards the moon, and the higher reflective power of clouds than that possessed by mere land and water. As the moon goes all the way round the sky every month, the same as the sun does in a year, and travels in nearly the same path, clearly it must also go north and south every month as the sun does. So in midsummer, when the sun runs high upon the meridian, we expect to find full moons running low, and likewise in midwinter the full moon always runs high, as almost everyone has sometimes or other noticed. This eastward or true orbital motion of the moon is responsible for another relation which soon comes to light when we begin to observe the moon. and that is the later hour of rising or setting each night. Our clock time is regulated by the sun, which also is moving eastward about 1 degree daily, or twice its own breadth. So the moon's eastward gain on the sun amounts to about 12 degrees daily, and 1 degree being equal to 4 minutes, the retarded time of moonrise or moonset each day amounts to very nearly 50 minutes on the average, though sometimes the delay will be less than half an hour, or at other times it will exceed an hour and a quarter. The season of least retardation of rising of the full moon is in the autumn, and so the moon that falls in late September and October is known as the harvest moon, and the next succeeding full moon is called the hunter's moon. Lunation is a term sometimes given to the moon's period from any definite phase round to the same phase again. Its length is the true period of the moon's revolution once round the earth, from the sun all the way round till it overtakes the sun again. The synodic period is another name for lunation, and its true length is 29 1/2 days, or very accurately 29 days, 12 hours, 44 minutes, 2.7 seconds, as calculated by astronomers with great exactness from many thousands revolutions of the moon. But if we want the true period of the moon round the earth as referred to a star, it is much shorter than this, amounting to only 27 days and nearly 1/3. This is called the moon's sidereal period or revolution, because it is the time elapsed while she is travelling eastward from a given star round to coincide with the same star again. If we study the moon's path in the sky more critically, we shall find that it does not quite follow the ecliptic or the sun's path, but that twice each month she deviates from the ecliptic, once to the north and once to the south of it, by roughly 10 times her own breadth. More accurately, this angle is 5 degrees, 8 minutes and 40 seconds, an almost invariable quantity, and it is therefore known as an astronomical constant, or the inclination of the moon's orbit to the ecliptic. So the moon's orbit must intersect the ecliptic, and as both are great circles in the sky, the points of intersection are known as the moon's nodes, one ascending and the other descending, and the nodes are 180 degrees apart. The figure of the moon's orbit is not circular, although it deviates only slightly from that form. But like the paths of all other satellites round their primary planets, and of the planets themselves round the sun, the moon's orbit is also an ellipse. The distance of the moon's centre from the earth's centre is therefore perpetually changing. The point of nearest approach is called perigee, and that of farthest recession apogee. The moon's distance from the earth is easier and simpler to be ascertained than that of any other heavenly body, because it is the nearest. An outline of the method of finding this distance is not difficult to present, and it resembles in every particular the method a surveyor uses to find the distance of some inaccessible point which he cannot measure directly. Up and down a stream, for example, he measures the length of a line, and from each end of it he measures the angle between the other end of the line and the object on the opposite side of the stream whose distance he wishes to find out. Then he applies the science of trigonometry to these three measures, two of angles and one the length of the side or base included between them, and a few minutes' calculation gives the distance of the inaccessible object from either end of the baseline. Now in like manner, to transfer the process to the sky, let the two ends of the base be represented by two astronomical observatories, for example Greenwich in the northern hemisphere and Cape Town in the southern. The baseline is the chord or straight line through the earth connecting the two observatories, and we know the length of this line pretty accurately, because we know the size of the earth. The angles measured are somewhat different from those in the terrestrial example, but the process amounts to the same thing, because the astronomers at the two observatories measure the angular distance of the centre of the moon from the zenith, each using his own zenith at the same time, and the same science of trigonometry enables them to figure out the length of any side of the triangles involved. The side which belongs to both triangles is the distance from the centre of the earth to the centre of the moon, and the average of many hundred measures of this gives 238,800 miles, or about 10 times the distance round the equator of the earth. We have said that the orbit in which the moon travels round the earth is practically a circle, but the earth's centre is found not at the centre of this orbit, but set to one side or eccentrically, so that the distance spanning the centres of the two bodies is sometimes as small as 221,610 miles at perigee and 252,970 miles at apogee. The moon's speed in this orbit averages rather more than half a mile every second of time, more accurately 3,350 feet a second, or 2,290 miles per hour. Once the moon's distance is known, its size or diameter is easy to ascertain. An angular measure is necessary, of course, that of an angle which the disc of the moon fills as seen from the earth. There are many types of astronomical instruments with which this angle can be measured, and its value is something more than half a degree, 31 degrees and 7 seconds. The moon's actual diameter figures out from this 2,133 miles, and it would therefore require nearly 50 moons merged in one to make a ball the size of the earth. Still, no other planet has a satellite as large in proportion to its primary as the moon is in relation to the earth, but the materials that compose the moon have less than 2/3 the average density of those that make up the earth, so that 81 moons fused together would be necessary to equal the mass or weight of the earth. If we figure out the force of attraction of the moon for bodies on its surface, we find it equals about 1/6 that of the earth. Athletes could perform some astounding feats there, miracles of high jump and hammer throw. Our interest in the moon's physical characteristics never wanes. Her nearness to us has always fascinated astronomer and layman alike. Early users of the telescope were readily led into error regarding the general characteristics of the lunar surface, and it is easy to see why they thought the smooth level plains must be seas, and gave them names to that effect which persist today, such as Mare Crisium, Mare Serenitatis, and so on. We may be sure that no water exists on the moon's surface, although some astronomers think that solid water, as ice or snow, may still exist there at a temperature too low for appreciable evaporation. Perhaps water, seas, and oceans were once there, but their secular dissemination and loss as vapour have gone on through the millions of years, till even the moon's atmosphere appears to have vanished completely. At least there is much better evidence of absence of atmosphere on the moon than of its presence. Not enough at any rate to equal 1,000th part of the barometric pressure that we have at the earth's surface. Frequent observations of stars passing behind the moon in occultations have satisfied astronomers on this point. We often say of the brilliant full moon, it is as bright as day. The photometer, or instrument for accurate comparison of lights, their amount and intensity, tells a different story. Indeed, if the entire dome of the sky were filled with full moons, we should be receiving only 1/8 of the light the sun gives us, and it would require more than 600,000 average full moons to equal the light radiation of the sun. Heat from the moon, however, is quite different. Early attempts to measure it detected none at all, but with modern instruments there is little trouble in detecting heat from the moon, though measurement of it is not easy. Much of the moon's heat is sun heat, directly reflected from the moon as sunlight is, but most of it is due to radiation of solar heat previously absorbed by the materials of the lunar surface. The actual temperature of the moon's surface suffers great variation. A fortnight's perpetual shining of the sun upon the lunar rocks would certainly heat them above the temperature of boiling water if the moon had an atmosphere to conserve and store this heat. But the entire absence of such an air blanket probably permits the sun's heat to be radiated away nearly as fast as it is received, leaving the temperature at the surface always very low. What physical influences the moon really has upon the earth must be very slight, barring the tides. But there is little hope of getting people generally to take that view, because the moon appears to be the planet of the people, and opinion that the moon controls the weather, for instance, amounts with them to practical certainty. More than likely all these notions are but legitimate survivals of superstition and astrology. In addition to the tides, Our magnetic observatories reveal slight disturbances with the swinging of the moon from apogee to perigee and back, but long series of weather observations have been faithfully interrogated with negative or contradictory results. If one believes that the moon's changes affect the weather, it is easy to remember coincidences and pass over the many times when no changes has taken place. The moon changes pretty frequently anyhow. As Young well puts it, a change of the moon necessarily occurs about once a week. All changes of the weather, for instance, must therefore occur within 3 or 4 days of a change of the moon, and 50% of them ought to occur within 46 hours of a change, even if there were no causal connection whatever. When we turn to the strongly diversified surface of the moon itself, we find much to rivet the attention, even with slender optical aid. Everyone wants to know how near the telescope, the biggest possible telescope, brings the moon to us. That will depend on many things. First of all, on the magnifying power of the eyepiece employed on the telescope, and eyepieces are changed on telescope just as they are on the microscopes, though not for the same reasons. The theoretical limit of the power of a telescope is usually considered as 100 for each inch of diameter or aperture of the object glass. A 40-inch telescope, such as that of the Yerkes Observatory, the largest refracting telescope in existence, should bear a magnifying power not to exceed 4000, but this limit is practically never reached, 1/2 of it, or 50 to the inch of aperture, being a good working limit of power, even under exceptional conditions of steadiness of atmosphere. If we reduce the effective distance of the moon from 240,000 miles to 100 miles, that is about the utmost that can be expected. But even at that distance we can make out only landscape details, nothing whatever like buildings or the works of intelligence. The larger relations of light and shade, so obvious to the naked eye on the moon, vanish on looking at it with the telescope, but we are at once captivated by the novel character of the surface and the seemingly great variety of detail that is clearly visible. As soon as the new moon comes out in the west, one may begin to gaze with interest and watch the terminator or sunrise line gradually steal over the roughened surface, bringing new and striking craters into view each night. Around the time of quarter moon, or a little past it, is one of the best times for telescopic views of the moon, because the huge craters Tycho and Copernicus are then in fine illumination. Close to the face of full moon is never a good time, because there are no shadows of the rough surface then, and its entire structure seems to be quite flat and uninteresting, except for the streaks or rills which radiate from Tycho in every direction, and are the only lunar features that are best seen near full. In a broad general way, the moon's surface, if compared with the earth's, differs in having no water. Our extensive oceans are replaced there by smooth, level plains, which were at first thought to be seas, and so named. There are 10 or 12 of them in all. Then we find mountain ranges, so numerous on the earth, relatively few on the moon. Those that exist are named, in part, for terrestrial mountain ranges, as the Alps, Caucasus, and the Apennines. But the nearly circular crater, a relatively rare formation on the earth, is seen dotted all over the moon in every size, from a fraction of a mile in diameter up to 60, 70, and in extreme cases 100 miles. No mere description of plains or mountains and craters affords an adequate idea of the moon's surface as it actually is. A telescopic view is necessary, or some of the modern photographs, which give an even better notion of the moon than any telescopic view. Many of the lunar craters are without doubt volcanic in origin, others seem to be ruins of molten lakes. Many thousands of the smaller ones appear as if formed by a violent pelting of the surface when semi-plastic, perhaps by enormous showers of meteoric matter. More than 30,000 craters cover the half of the lunar surface visible from the earth, and hundreds of them are named for philosophers and astronomers. Measurement of the height of lunar mountains have been made in numerous instances, especially when their shadows fall on plains or surfaces that are nearly level, so that the length of the shadow can be measured. In general, the height of lunar peaks is greater than that of terrestrial peaks. owing probably to the lesser surface gravity of the moon. About 40 lunar peaks are higher than Mont Blanc. Most astronomers regard it as certain that no changes ever take place on the moon. Probably no very conspicuous changes ever do. Some, however, have made out a fair case for comparatively recent changes in surface detail. Extreme caution is necessary in drawing conclusions, because the varying changes of illumination from one phase to another are themselves sufficient to cause the appearance of change. At intervals of a double lunation equal to 59 days, 1½ hours, the Terminator goes very nearly through the same objects, so that the circumstances of illumination are comparable. In Mare Serenitatis, the little crater named Linne was announced to have disappeared about a half-century ago. Subsequently it became visible again, and other minor changes were reported, perhaps due to falling in of the walls of the crater. If one were to visit the moon, he must needs take air and water along with him, as well as other sustenance. No atmosphere means no diffused light. We could see nothing unless the sun's direct rays were shining upon it. Anyone stepping into the shadow of a lunar crag would become wholly invisible. No sound, however loud, could be heard. Sound, in fact, would become impossible. A rock might roll down the wall of a lunar crater, but there would be no noise, though we should know what had happened by the tremor produced. So slight is gravity there that a good ball player might bat a baseball half a mile or more. Looking upward, all the stars would be appreciably brighter than here, and visible perpetually in the daytime as well as at night. If one were to go to the opposite side of the moon, he would lose sight of the earth until he came back to the side which is always turned towards the earth. Even then the earth would never rise and set at any given place, as the moon does to us, but would remain all the time at about the same height above the lunar horizon. The earth would go through all the phases that the moon shows to us here, full earth occurring there when it is new moon here. Our globe would appear to be nearly 4 times broader than the moon seems to us. Its wide polar caps of ice and snow, its dark oceans and the vast cloud areas would be very conspicuous. Faint stars, the zodiacal light and the filmy solar corona would be visible, probably even close up to the sun's edge, but although his rays might shine upon the lunar rocks without intermission for a fortnight, probably they would still be too cold to touch with safety. On the side of the moon turned away from the sun, the temperature of the moon's surface would fall to that of space, or many hundred degrees below zero. End of chapter 28.